Right now, you are inside something so large that even light moving as fast as anything in the universe can move would need 100,000 years to cross it. That is the Milky Way, and you are somewhere near the edge of one of its spiral arms on a small planet about to fall asleep. But the strangest thing about the universe is not its size. It's what happens at the other end of the scale, in the space smaller than an atom, smaller than a nucleus, at the boundary where matter and light stop being different things. There is a moment physicists call annihilation. An electron meets its mirror image. They don't collide, they don't shatter. They vanish, replaced by two beams of light moving in opposite directions, each carrying exactly the energy those particles used to be. No fragment, no residue, just radiation. That conversion matter becoming light completely with nothing left over is the question we're following tonight. Because hidden inside it is something that very few people have stopped to ask. If matter can become light that cleanly, what was matter made of to begin with? There is something that happens between two particles when they meet, and physics has never fully recovered from it. An electron and its mirror twin come together. In the span of one quiet exhale, both of them cease to exist as matter. What replaces them are two beams of gamma radiation, traveling in exactly opposite directions, each carrying precisely 500,000 electron volts of energy. Not scattered, not absorbed, converted, with a precision that leaves no remainder and no room for error. The process runs in reverse, with equal exactness. In the early 1930s, experimenters in Cambridge discovered that a high-energy photon passing near an atomic nucleus could spontaneously produce an electron and a positron from nothing but light and proximity. The energy threshold was specific and absolute. Below it, nothing happened. At it, matter appeared. They called it pair creation. What it revealed was a symmetry so precise it reshaped the foundations of physics. Matter and light are not two separate substances governed by separate laws. They are two states of the same underlying quantity, interconverting at a fixed exchange rate that never fluctuates. Think of it like water and ice. Same molecules, entirely different form, and the transition between them is governed entirely by energy. At the scale of particles, nature runs the same logic, only the stakes are different. What crosses the threshold is not temperature, but frequency. When a photon's frequency climbs high enough, it carries sufficient energy to fold into matter. When matter finds its mirror image, it unfolds back into light. The boundary between particle and wave is not a wall. It is a reversible door, and energy is the key that opens it from either side. This is what sits underneath the question we're following tonight. If light can become an electron with perfect reproducibility every time, at the same threshold, producing the same mass and the same charge, then the electron is not something fundamentally different from light. It is light in a particular configuration. The question is what that configuration looks like. That question lingered for decades. Too unconventional for mainstream pursuit, too persistent to disappear. In 1997, two physicists named Williamson and Vandermark decided to approach it not as philosophy, but as a constraint problem. The electron has known properties, a specific mass, a specific charge, a specific magnetic moment, and a rotational behavior called spin 1/2 that has no classical analog. They asked whether a single photon, confined to a closed path, could reproduce all four simultaneously. Their answer was a torus. a photon bent into a ring whose circumference equals the electron's Compton wavelength, the precise scale, identified by Arthur Compton in the 1920s, at which radiation begins to acquire matter-like properties. Not chosen arbitrarily. Chosen because it is the only scale at which the energy of a photon matches the rest mass of an electron. Below that circumference, the photon carries too little energy to form the structure. Above it, the geometry cannot sustain itself. At exactly that scale, the numbers close. Inside the ring, the electromagnetic fields fold in two directions simultaneously around the torus and through it. That dual motion produces a rotational symmetry requiring two full traversals to return to the original configuration, precisely the 4π behavior that defines spin, half particles, the behavior Wolfgang Pauli had encoded mathematically in 1927 without being able to explain its physical origin. The torus does not add this property. It generates it from geometry alone. Charge emerges the same way. When a circularly polarized wave wraps onto the toroidal surface, its electric field vectors develop a global orientation leaning systematically inward across the entire structure. From any external distance, that lean produces a field indistinguishable from that of a point charge. Reverse the direction of circulation, and the lean reverses inward becomes outward, negative becomes positive. The electron and the positron are not two different substances. They are the same geometry, running in opposite directions. What makes this harder to set aside is that similar field structures have been observed in nature. In high-temperature plasmas, electromagnetic fields spontaneously organize into stable toroidal knots that resist external disruption. In nonlinear optical experiments, light pulses have been observed trapping themselves, holding their shape against dispersion, the way a smoke ring holds itself in still air, sustained not by any container, but by the internal balance of its own motion. Self-confined light was once considered a theoretical curiosity. It has since been produced in the laboratory. The vacuum itself participates. Julian Schwinger calculated in 1951 that beyond a specific electric field strength, one that modern laser facilities are beginning to approach, the quantum vacuum becomes unstable and spontaneously generates electron-positron pairs. The vacuum has a measurable threshold beyond which it can no longer remain empty. It behaves like a medium, under stress like a drumhead, that yields at a specific tension, not before and not after. And a medium with a yield threshold is precisely the kind of environment where a photon's field might find a radius at which outward electromagnetic pressure and inward vacuum resistance reach equilibrium. That radius, when calculated, falls at the Compton scale. None of this arrived without preparation. Louis de Broglie argued in the early 1920s that every particle carries an internal frequency, a hidden oscillation tied to its rest mass, ticking at a rate proportional to its energy. For the electron, that frequency is approximately 1.2 times 10 to the 20th cycles per second, a rhythm so fast it completes more oscillations in a single second than there are stars in the observable universe. Most physicists set the idea aside. Then precision measurements of the Lamb shift in 1947 revealed that the electron's energy levels are nudged by fluctuations in the vacuum, meaning the electron is not isolated from empty space, but continuously coupled to it, responding to quantum field activity the way a tuning fork responds to the resonance of a room. And Data from magnetic resonance experiments in the 1960s showed that the electron's anomalous magnetic moment, the tiny deviation of its magnetic behavior from classical prediction, carries fingerprints of internal dynamics that a true point particle cannot possess. Not contradictions, not conclusive proof. Small openings, each one consistent with something more structured than a dimensionless point living quietly at the center of every atom in the universe. Williamson and Vandermark did not claim to have found the electron's true nature. They demonstrated compatibility, a geometry that satisfies the Compton threshold, reproduces spin 1/2 without additional assumptions, derives charge from field orientation rather than postulating it, and avoids the infinite self-energy that a perfect point cannot escape. Whether the torus is real or a useful approximation of something deeper, it does what the point particle model quietly refuses to do. It offers a reason why the electron has the properties it has, rather than simply recording that it does. The Standard Model describes the electron as a point because no experiment has resolved anything smaller. That is an honest statement about measurement. It is not a statement about structure. Two particles meet. Two beams of light remain. The accounting is perfect, the symmetry is exact, and the boundary between matter and radiation dissolves so completely that the question it leaves behind has no clean answer. Not what the electron does, what it is, and whether light, curved tightly enough, might already be the answer waiting in plain sight inside every atom, every molecule, every breath. Physics has a peculiar talent for building bridges over chasms it refuses to look down into. The electron is called a point, not small point. Zero size, zero volume, zero interior, and in the same breath, physics assigns it a mass, a charge, a magnetic moment, and a rotational behavior called spin, half that has no classical equivalent. Compress any amount of energy into zero volume, and the mathematics of classical electromagnetism returns one answer: infinite field density, infinite self-energy, infinite everything. The electron ignores this. It has a finite mass. It exists. And the chasm between those two facts has been quietly open for over a century. The trouble begins with the electric field itself. Surround any charged object with an electromagnetic field, and that field stores energy the way a compressed spring stores mechanical energy, locked into its geometry, ready to release. The closer you move toward the charged object, the stronger the field, and the more energy it holds. For a sphere with finite radius, this energy converges to a manageable number. For a perfect point with radius 0, the energy stored in the field at infinitesimally small distances grows without limit. The mathematics doesn't round off. It doesn't saturate. It simply keeps climbing toward infinity as the distance approaches 0. Classical electrodynamics, applied honestly to a point electron, predicts that the electron's own field should contain infinite energy, which is another way of saying it predicts something that cannot exist. Physicists in the 1940s developed a procedure to manage this. Renormalization. They called it a method of subtracting the infinities from the calculation in a controlled way, leaving behind finite testable predictions. The predictions it produced were extraordinarily accurate. But the physicist who helped construct it described the procedure the way a mechanic might describe a car that runs perfectly while leaking oil. It works, he said, but we are sweeping something under the rug, and we know it. Renormalization is not an explanation of why the electron's energy is finite. It is a method of proceeding as if the infinity were not there. Spin deepens the problem. Samuel Gaudsmit and George Uhlenbeck identified spin, half, in 1925, while analyzing the spectral lines of hydrogen narrow bands of light emitted when electrons change energy levels inside atoms. The pattern of those lines could only be explained if each electron carried an intrinsic angular momentum, a kind of built-in rotation. The obvious interpretation was a spinning sphere of charge. But when physicists calculated what spin rate would be required to produce the electron's measured magnetic moment, they found that the surface of that sphere would need to move faster than the speed of light. Not slightly faster, many times faster. The spinning sphere was abandoned. The electron became a point again. But the magnetic moment remained measurable, precise, and demanding an explanation that a point cannot provide. Measurements using Penning Trapp's instruments that suspend individual electrons in carefully balanced electromagnetic fields for days at a time have confirmed the electron's magnetic moment to more than 10 decimal plus. To understand what that precision means, if you measured the distance from New York to Los Angeles to 10 decimal places, you would know it to within a fraction of the width of a single atom. The measurement is that exact. And what it reveals is that the electron's magnetic behavior deviates from the classical prediction by a tiny but specific amount, an anomalous correction that quantum electrodynamics accounts for through interactions with virtual particles in the vacuum. A point particle has no interior, yet its magnetic behavior carries signatures of something dynamic happening inside. Willis Lamb and Robert Rutherford made this stranger still in 1947. Measuring hydrogen's energy levels with new precision tools developed during wartime radar research, they found a tiny discrepancy between two states that quantum theory predicted should be identical. The difference was real, reproducible, and impossibly small, smaller than the width of a single spectral line, detectable only because their instruments were tuned to microwave frequencies where such fine distinctions become audible, the way a piano tuner hears the slow beating of two notes that are nearly, but not quite, in unison. What caused the shift was the electron's interaction with the quantum vacuum. The vacuum fluctuates, virtual particle pairs appear and vanish constantly, and those fluctuations press against the electron, nudging its energy levels in measurable ways. A perfectly structureless point would have no surface to press against, no geometry to respond to, no mechanism by which a fluctuation could leave a mark. The Lamb shift leaves a mark. Paul Dirac had already seen the outlines of this paradox from a different angle. In 1928, he wrote an equation, unifying quantum mechanics with special relativity, that produced the electron's spin and magnetic moment as natural mathematical consequences. No spinning sphere required, no assumed internal structure. The equation was one of the great achievements of 20th century physics. It also predicted the existence of antimatter 4 years before Carl Anderson observed the first positron in a cloud chamber photograph, watching a particle curve the wrong way through a magnetic field and realizing the track belonged to something that had never been seen before. Dirac's equation describes with extraordinary precision how the electron behaves in every situation we can construct. It says nothing about what the electron is. The question it sidesteps is the same question renormalization sidesteps, and the same question the spinning sphere sidesteps. Scattering experiments ran directly into this wall throughout the second half of the 20th century. At facilities like SLAC in California, physicists accelerated electrons to enormous energies and fired them at target nuclei, watching how the particles deflected. The deflection pattern carries information about structure the same way sonar maps the shape of a submarine by analyzing how sound waves bounce back. If the electron had internal parts, the scattering pattern would reveal them at high enough energies. Experiment after experiment showed nothing. Point-like behavior, down to distances roughly 1/10,000,000th the size of a proton, a scale so small that if an atom were expanded to the size of the entire Earth, that distance would still be smaller than a grain of sand. The electron hid perfectly, or there was nothing to hide. The experiments could not distinguish between the two. What the experiments could not resolve was the self-energy problem. Probing smaller distances requires higher energy probes. Higher energy probes eventually carry enough energy to create new particles, including electron-positron pairs, which then interact with the electron being measured and alter the result. At the scale of the electron's Compton wavelength, the act of measurement begins to produce new matter, contaminating the very observation it was meant to clarify. The deeper you try to look, the more the looking changes what is there. It is not a failure of instruments. It is a limit written into the structure of quantum mechanics itself. The 1950s produced one serious attempt to escape this. Theorists explored extended electron models configurations in which the electron occupied a small but finite volume, with internal electromagnetic stiffness preventing collapse. The idea was physically motivated and mathematically tractable. It collapsed under special relativity. Any extended object in relativistic motion develops internal stresses that no known force could stabilize the model required, introducing new, undetectable binding forces simply to keep the structure from flying apart, and a theory built on undetectable forces explains nothing. The electron returned to being a point because no alternative survived the full set of constraints. Not because the point model was satisfying, because everything else broke sooner. Astrophysical observation has since compounded the tension quietly. Instruments measuring gamma-ray emissions near pulsars and black holes have detected electron-positron pairs forming from pure energy in intense magnetic environments, pairs that appear in exactly the quantities quantum field theory predicts, at exactly the energy thresholds it specifies. Electrons are being created from radiation reproducibly in some of the most extreme environments the universe produces. If the electron has no internal structure, if it is simply a point excitation of the electron field with no geometry, no organization, no encoded pattern, then what exactly does pair creation assemble? What does annihilation disassemble? The field theory answer is that these are the wrong questions. But the questions keep forming anyway, at the edge of what the formalism can silence. Ultra-intense laser experiments are narrowing that edge. Research groups working with laser fields intense enough to heat matter to temperatures found only in stellar interiors have begun observing nonlinear vacuum responses, the vacuum behaving not as empty space but as a medium that bends, refracts, and responds to electromagnetic stress. These effects are faint at current intensities, but they are real and growing. They are the first laboratory glimpses of the same physics that produces electron-positron pairs near the Schwinger threshold. And they confirm that the vacuum surrounding every electron is not passive. It responds. Something in the electron's field engages it. A point has no field at finite distances that could do this without diverging. Something must regulate the interaction before it reaches the singularity. The contradictions do not cancel each other. They accumulate. infinite self-energy held at bay by mathematics. Spin with no mechanism for rotation. A magnetic moment precise to 10 decimal places with no interior to generate it. A Lamb shift that requires the electron to have something the vacuum can press against. Point-like scattering at every scale we can reach, alongside pair creation that requires assembling something specific at a fixed energy threshold every time. Each observation, taken alone, can be absorbed into the formalism. Taken together, they form a portrait of something that behaves like a point from the outside, while insisting, through every precision measurement ever made, that something structured is operating within. Physics built a bridge across that chasm. Renormalization, quantum field theory, the Standard Model, all of them cross it cleanly and produce predictions of extraordinary accuracy. But none of them look down. None of them answer what sits at the bottom. Not in the equations that cross the gap, but in the scale that marks its edge, a length so precisely defined that it appears in pair creation, in scattering limits, in vacuum thresholds, and in the toroidal model alike, as though nature placed a signpost there, quietly, for anyone willing to read it. Arthur Compton walked into his laboratory in 1923 with a straightforward question and walked out with one that has never been fully answered. He aimed a beam of X-rays at a block of carbon and measured what came out the other side. The setup was simple enough that a careful undergraduate could replicate it today. What he found was not simple at all. The photons that scattered off the carbon atoms came back with longer wavelengths than they went in with. Not randomly longer by a precise amount that depended only on the angle of scattering, governed by a single constant that appeared nowhere in classical wave theory. Classical theory said this should not happen. Waves do not lose energy by bouncing. Wavelength is not something a wave gives away in a collision. And yet the photons came back changed, consistently, reproducibly, with the same shift at the same angles every time. What Compton had uncovered was not just a scattering result. He had found a boundary. The constant that described his shift, later named the Compton wavelength of the electron, marks a scale so fundamental that it governs every transition between light and matter anywhere in the universe. To give that scale some human proportion, the Compton wavelength is roughly 2.5 trillionths of a meter. If a single atom were expanded to the size of a football stadium, the Compton wavelength would be roughly the size of a golf ball sitting at midfield. Small by atomic standards, but not zero. And never zero. Below that scale, something changes. A photon whose wavelength is longer than the Compton wavelength carries too little energy to produce matter. It can scatter, it can warm, it can ionize, but it cannot create an electron. Compress that photon until its wavelength reaches the Compton scale, and something different becomes possible. The photon now carries exactly enough energy to fold into an electron-positron pair. Not approximately enough. Exactly enough. The exchange rate between light and matter is fixed at precisely that wavelength, and it has never once been observed to fluctuate. This is what makes the Compton wavelength more than a parameter from a scattering experiment. It is the toll gate between radiation and matter, the precise scale at which photons stop being purely wave-like and begin carrying the energy required to become something with mass. Werner Heisenberg saw the deeper implication of this in 1927. His uncertainty principle said that confining a particle to a smaller and smaller region requires injecting more and more energy into the system. Push that confinement below the Compton scale, and the injected energy exceeds the threshold for pair creation. New electron-positron pairs spontaneously appear, and the measurement is contaminated by matter that did not exist a moment before. You cannot probe below the Compton wavelength without the probe itself becoming a particle factory. The act of looking changes what is there, not because of technical limitation, but because of physics, because at that scale, the distinction between the observer and the observed begins to dissolve. Think of it like trying to inspect the surface of a soap bubble with a flashlight. A dim light leaves the bubble intact but reveals nothing. A bright enough light to actually see the surface carries enough energy to destroy the bubble before the image forms. You can have the bubble, or you can have the measurement. Not both. The Compton scale is the point at which this trade-off becomes absolute and irreversible for the electron. Here is what this means for the point-particle model. A mathematical point has no preferred length scale. A point is the same at every distance. It has no built-in radius, no natural circumference, no scale it insists on. But the electron behaves as though it has a scale. It will not give up. Every time matter is created anywhere in the universe, in a particle accelerator in Geneva, in the accretion disk of a black hole a billion light-years away, in the plasma of the early universe, 3 minutes after the Big Bang, the electron appears at the same mass, with the same charge, and with the same Compton threshold governing its creation. The universe has been running this experiment continuously for nearly 14 billion years, and the scale has never shifted. Niels Bohr resisted Compton's results at first. In the months after publication, he argued that classical wave theory could still be preserved, that the wavelength shift might have another explanation, one that did not require treating light as a particle. Compton traveled to Copenhagen, carrying physical photographic plates from his scattering apparatus. He laid them out one by one. Each plate showed the same shift, the same angular dependence, the same constant. Bohr studied the photographs for a long time. When he finally looked up, his resistance had simply run out of places to go. The data was the data. The boundary was real. Gamma-ray telescopes observing the sky have confirmed this boundary from the other direction. When electrons and positrons annihilate near neutron stars and at the centers of galaxies, they produce gamma-ray photons at a very specific energy, the energy corresponding exactly to the electron's rest mass, set precisely by the Compton scale. This annihilation signal has been detected across vast distances of space and across billions of years of cosmic history. It has never shifted. The Compton scale in a galaxy that formed 10 billion years ago is the same Compton scale in a laboratory in Geneva today. The James Webb Space Telescope observes hot plasmas in the earliest galaxies, environments where electrons and photons continuously exchange energy at the highest temperatures the post-Big Bang universe produced. The threshold governing those exchanges is the same one Compton measured in St. Louis in 1923 with a carbon block and a photon detector. The universe has not updated this number. It does not appear to have the option. Quantum field theory absorbs this gracefully. It describes the electron as a point excitation of a quantum field, and the Compton wavelength enters the theory as a natural boundary beyond which localizing the excitation becomes physically meaningless, not because the math breaks down, but because the process of localization generates new particles and changes the state being measured. The point-particle description survives because every scattering experiment probes momentum, not ontology. Scattering tells you how something deflects. It does not tell you what something is. What it cannot explain is why the boundary exists at all for a true point. A point has no circumference. It has no internal path length. It has no characteristic scale that would determine a threshold energy for its own creation. Yet the electron insists on one. Not approximately, not as a convenient parameter, as a hard physical boundary that no process in the universe has ever crossed from the wrong side. Williamson and Vandermark took this seriously as a geometric clue. In their model, the Compton wavelength is not an external parameter imposed on the electron from quantum mechanics. It is the circumference of the toroidal path the trapped photon follows. The loop has a specific size because only at that circumference does the photon's energy match the electron's rest mass too small and the energy exceeds the threshold, triggering pair creation instead of confinement, too large and the structure cannot sustain itself. The Compton wavelength is the circumference where the balance holds, where energy and geometry agree, where a photon can stop being a photon and start being something that stays. Whether that picture is precisely correct, the Compton scale itself is not speculative. It is written into every particle creation event in the observable universe, every annihilation line ever measured, every threshold ever confirmed. The electron is not infinitely compressible. It is not infinitely localizable. It carries a scale it will not surrender. In every environment, at every energy, across every distance that telescopes have ever reached. That scale is a fact. What it is a fact about whether it is the circumference of something real or simply the deepest limit physics can reach, before the act of measurement becomes the thing being measured, is the question that opens just ahead. There is a peculiar thing that happens when you take a corkscrew and bend it into a circle. Not physically, as a thought experiment. A corkscrew moves forward in a straight line while rotating around its own axis. Both motions are independent, the forward travel and the spin. Now, imagine bending that forward path into a complete loop. The moment the path closes on itself, the two motions are no longer independent. The rotation and the curvature become entangled, each affecting the other, neither able to proceed as if the other does not exist. This is, in stripped-down form, what Williamson and Vandermark proposed for the electron. A circularly polarized photon light whose electric field rotates at constant magnitude as it travels bent into a closed toroidal path so that its own rotation and its orbital motion become permanently coupled. And from that coupling, something unexpected emerges, properties that look, from the outside, exactly like charge, spin, and magnetic moment. To understand why this is not as arbitrary as it sounds, start with what circular polarization actually is. A standard light wave oscillates the electric field points up, then down, then up again, tracing a flat back and forth rhythm as the wave moves forward. A circularly polarized wave does something different. The electric field rotates continuously, steadily, sweeping around the axis of travel the way the hand of a clock sweeps around its face, but in 3 dimensions, always perpendicular to the direction of motion. The field magnitude never changes. Only the direction rotates. This gives the wave a handedness, a left-handed or right-handed twist, built into the geometry of the wave itself. On a straight trajectory, this handedness is invisible from a distance. The wave passes through space, rotates, and continues forward. Nothing about its behavior suggests a particle. Nothing about it suggests charge, or spin, or a preferred location in space. Bend that trajectory into a loop, and everything changes. The rotating electric field can no longer travel indefinitely in one direction. It must curve. And as it curves, the handedness of its rotation, that left or right-handed twist, begins to interact with the curvature of the path itself. The two motions merge into something more complicated. The field rotates around the axis of the torus while simultaneously sweeping along the circumference of the loop. Picture a bicycle tire rolling around a circular track. The wheel spins around its own axle, while the axle itself traces a circle. Both rotations are happening simultaneously, and they are geometrically linked. Change one, and you change the other. The electron's torus works by the same principle, except the two motions are not mechanical, but electromagnetic, locked together by Maxwell's equations rather than by physical contact. From that coupling, spin 1/2 appears. Spin 1/2 is one of the stranger properties in all of physics. A normal rotating object, a wheel, a planet, a spinning top, returns to its original orientation after one full rotation. Spin 1/2 particles do not. Rotate an electron through a full 360 degrees, and it is not back where it started. Its quantum state has inverted, flipped into its mirror configuration. Only after a second full rotation, 720 degrees total, does it return to its original state. This behavior has no analog in everyday experience. It was first revealed in 1922, when Otto Stern and Walther Gerlach sent silver atoms through a non-uniform magnetic field and watched the beams split into exactly two discrete paths, not a smear, not a continuum, but two clean lines, one for each spin orientation. The universe was announcing something about internal angular momentum that classical physics had no language to describe. The toroidal geometry produces this naturally. Trace any directional quantity, any arrow representing the orientation of a field along the surface of a torus while it simultaneously rotates around the torus's core. Follow it through one complete orbit around the loop. The arrow does not return to its starting orientation. It arrives inverted, pointing in the opposite direction. Complete a second orbit, and it returns to where it began. Two full traversals to complete one cycle. 720 degrees, not 360. The torus does not approximate spin. 1/2, it generates the exact rotational rule from geometry, without any additional assumptions built in by hand. The magnetic dipole moment follows from the same structure. Any moving electric charge generates a magnetic field that wraps around the direction of motion. This is one of the foundational results of electromagnetism, established in the 19th century and confirmed by every motor, generator, and MRI machine ever built. In a straight circularly polarized wave, the magnetic field wraps around the direction of travel and keeps going, spreading outward indefinitely. In the toroidal loop, the wave has no indefinite direction. The magnetic curls that would have spread outward are forced to close on themselves, folding into stable loops that wrap around the core of the torus, contained by the geometry of the closed path. The result is a magnetic dipole, a north-south field structure centered on the toroidal ring with the correct orientation and topology to match the electron's measured magnetic moment. Not an approximation. The same structure, produced by the same mechanism, at the same scale. Electric charge emerges by a subtler process, and it is the one that surprised Williamson and Vandermark most. When a circularly polarized wave wraps onto the surface of a torus, the rotating electric field vectors cannot distribute themselves symmetrically. The inner surface of the torus has a smaller circumference than the outer surface, the same reason that a road's inner lane is shorter than its outer lane on a circular track. The field vectors are packed more densely on the inside and more spread out on the outside, and this asymmetry forces the net electric field to develop a global directional lean, either pointing systematically inward toward the torus's center or systematically outward away from it. From any distance large compared to the torus itself, that global lean is indistinguishable from the field produced by a point charge. Inward lean produces the field pattern of negative charge. Outward lean produces the field pattern of positive charge. Charge, in this framework, is not a primitive property assigned to the particle at the beginning. It is the directional consequence of fitting a rotating wave onto a curved, asymmetric surface. The geometry forces the asymmetry. The asymmetry produces what we call charge. This also determines the relationship between the electron and the positron. They are not different particles. They are the same toroidal structure with opposite circulation, one photon bending clockwise around the loop, the other counterclockwise. Reverse the direction of the internal wave, and the lean of the electric field reverses with it. Negative becomes positive. Electron becomes positron. The mass is identical because the circumference of the loop set by the energy of the trapped photon does not change when the direction reverses. Only the orientation changes. The size of the torus is not a free parameter. The trapped photon exerts outward electromagnetic pressure on the loop, trying to expand it. The vacuum pushes back not as empty space, but as a medium with measurable nonlinear resistance to extreme electromagnetic curvature, a resistance that becomes strongest at the scale of the electron's Compton wavelength. Think of it like inflating a tire inside a sleeve that resists expansion. The tire finds the radius where its internal pressure matches the sleeve's resistance and holds there. The electron's torus finds the circumference where outward photon pressure and inward vacuum resistance balance, and that circumference is the Compton wavelength, the same scale that governs pair creation, annihilation, and every threshold at which matter is born from light. The size is not chosen. It is negotiated between the photon and the vacuum, and the negotiation always ends at the same number. Erwin Schrödinger identified a hint of this internal motion in 1931. Solving the relativistic wave equation for the electron, he found that the electron's position is not fixed even when its average momentum is zero. It undergoes rapid, tiny oscillations he called Zitterbewegung, from the German for trembling motion. The frequency of those trembles matched the electron's rest mass energy, exactly the same energy as the trapped photon in the toroidal model, oscillating at the same characteristic rate. Schrödinger could not explain what was trembling or why. The toroidal picture offers a candidate, the two coupled rotations of a confined electromagnetic wave, producing the appearance of rapid internal oscillation from the outside. What makes this worth taking seriously is not that each property is approximately reproduced. It is that all of them are reproduced simultaneously, from the same geometry, without separate mechanisms for each one. Spin does not require one assumption and charge another, and magnetic moment a third. They all follow from the same closed path, the same coupled rotations, the same balance between photon pressure and vacuum resistance. The Standard Model achieves the same predictions through a different route, treating the electron as a point excitation of a quantum field, adding spin and charge as fundamental labels, and computing interactions through the machinery of quantum electrodynamics. It works with extraordinary precision. What it does not do is explain why the electron has these properties, rather than simply recording that it does. The torus offers an explanation. Whether that explanation is the correct one is a question the available experiments cannot yet answer. But what it demonstrates is that geometry alone, the specific shape of a closed electromagnetic path, is sufficient to generate the defining properties of matter from the behavior of light. Charge from curvature. Spin from topology. Magnetism from field closure. Stability from geometric locking. And size from the negotiation between a photon and the vacuum that contains it. None of these required a new force, a new particle, or a new law of physics. Only a shape. And that shape has one more consequence that has not yet been examined. A consequence that becomes visible the moment you ask what happens when the direction of circulation reverses and the entire structure becomes its own mirror image. In 1932, a physicist named Carl Anderson was studying cosmic rays, high-energy particles, raining down from space by letting them pass through a cloud chamber filled with supersaturated vapor. Particles moving through the chamber left thin trails of condensation, the way a jet leaves a contrail across a clear sky. A magnetic field bent those trails into curves, and the direction of the curve revealed the particle's charge. Anderson saw a trail that curved the wrong way. Not wrong by a little. Not ambiguous. Wrong in the only way that mattered. The particle had the same mass as an electron, the same trail thickness, the same behavior in every respect except the magnetic field bent it in the direction reserved for positive charge. He checked the apparatus. He checked his measurements. He ran more exposures. Every new plate confirmed it. Something had passed through his chamber that was identical to the electron in every property except one, and that one property was reversed as completely as a mirror image reverses left and right. He had found the positron, the first antiparticle ever directly observed. Paul Dirac had predicted its existence 4 years earlier. From pure mathematics, his relativistic equation for the electron produced 2 solutions, one for negative charge and one for positive, and Dirac trusted the math enough to insist that both must exist in nature. Anderson's cloud chamber confirmed it. Matter had a mirror, and the mirror was not a different substance. It was the same substance running in reverse. This is the moment the toroidal model becomes most compelling, not as an abstract geometry, but as a direct explanation for what Anderson saw. The toroidal electron is a photon circulating in a closed loop. That circulation has a direction. The wave rotates clockwise or counterclockwise as it travels around the ring. Everything the electron is, its charge, its magnetic moment, its spin orientation flows from that directional choice. The charge is negative because the internal circulation forces the electric field to lean inward. The magnetic moment points in one specific direction because the circulating current wraps the magnetic field around the torus in one specific orientation. Reverse the circulation, and every one of those consequences reverses with it. The electric field lean flips from inward to outward. Negative charge becomes positive. The magnetic field wraps the other way. The magnetic moment inverts. The spin state changes sign. And the mass stays exactly the same, because mass depends on the circumference of the loop and the energy of the trapped photon, neither of which changes when the direction of travel reverses. The same geometry, the same size, the same energy. Everything the same except the direction. What Anderson photographed in 1932, in other words, was a torus running backward. Think of it like a vinyl record. The same physical groove, the same physical disc, the same physical needle but played in reverse. The music comes out mirror inverted, every acoustic pattern flipped in time. The record does not become a different object when you play it backward. It becomes the same object, expressing itself in the opposite direction. The positron, in the toroidal model, is the electron's groove played backward, the same structure, the same loop, the same trapped energy, with every directional property inverted by the simple reversal of circulation. This resolves something that the Standard Model leaves unexplained. In the Standard Model, the electron and positron are described as separate particle and antiparticle, two distinct field excitations that happen to have equal mass and opposite charge. The equality of their masses is an empirical fact, confirmed to extraordinary precision by experiments comparing their cyclotron frequencies in pinning traps. But the Standard Model does not explain why the masses must be equal. It simply observes that they are. The toroidal model explains it structurally. The masses are equal because the circumference of the loop is the same for both. The circumference is set by the energy of the trapped photon, which equals the electron's rest mass energy in both configurations. The direction of circulation has no effect on the loop's size. So, the masses are not approximately equal, not coincidentally equal. They are necessarily equal, as a geometric consequence of the structure. The same logic extends to spin. The torus supports exactly two stable circulation directions for its internal wave, clockwise and counterclockwise. Each direction produces a distinct angular momentum orientation, what quantum mechanics calls spin up and spin down. These are not two different particles. They are the two orientations of the same geometry. The same way a compass needle pointing north and pointing south are not two different needles, but one needle in two possible states. When Otto Stern and Walther Gerlach sent silver atoms through a non-uniform magnetic field in 1922 and watched the beam split into exactly two discrete paths, they were observing this duality directly. Not a smear of angles, not a continuum, two paths, precisely. The universe was insisting that something inside the electron had exactly two possible orientations, no more, no less. The torus explains why: two circulation directions, two spin states, and the geometry allows nothing in between. The stability of both configurations follows from the same topological argument. The electromagnetic fields inside the torus reinforce each other along the closed path, the electric and magnetic components cycling in phase, supporting the curvature of the loop. This constructive alignment persists regardless of which direction the wave circulates. Reversing the circulation does not disrupt the alignment, it preserves it, with every field relationship intact but mirrored. The reverse torus is just as stable as the forward one, not by coincidence, but because stability depends on the wave fitting constructively into the loop, and a reversed wave fits just as well as a forward one. This is why matter and antimatter are produced in equal amounts whenever pair creation occurs. When an intense electromagnetic field pushes the vacuum past its stability threshold, the vacuum does not produce electrons alone or positrons alone. It produces both simultaneously, in matched pairs, one running clockwise, one running counterclockwise. The vacuum has no preference for one circulation direction over the other. Both are equally valid solutions to the same balance between photon pressure and vacuum resistance. So both appear together. their properties equal and opposite, their existence the natural consequence of a geometry that supports two stable orientations with perfect symmetry. Observations near pulsars and black holes confirm this symmetry at cosmic scales. In the intensely magnetized regions surrounding neutron stars, where the electromagnetic field strength approaches the level at which vacuum stability breaks down, gamma-ray telescopes observe bursts of electron-positron pairs emerging from regions of strong field curvature. The pairs always appear with opposite magnetic signatures, never one without the other, never in unequal numbers that would suggest the two configurations are independent objects rather than mirror states of the same structure. The symmetry is exact. It has never been observed to break. The same annihilation symmetry appears in every gamma-ray observation of matter-antimatter recombination. When an electron and a positron meet, their loops merge and cancel forward circulation and reverse circulation, annihilating each other, their combined energy releasing as two photons traveling in exactly opposite directions, each carrying exactly the energy the loop's circumference required to maintain itself. The accounting is perfect because the structure is perfect. Two mirror geometries, combining to zero, returning cleanly to the light they came from. There is something worth pausing over in all of this. The universe contains matter and antimatter in nearly equal proportions at the moment of pair creation. The fact that the observable universe today is dominated by matter, that we exist as matter, rather than having annihilated with equal amounts of antimatter shortly after the Big Bang, is one of the deepest unsolved problems in cosmology. Some small asymmetry must have tipped the balance toward matter in the early universe, enough of an excess to survive after all the matched pairs annihilated. The toroidal model does not resolve this asymmetry. No model does, not yet. But it does explain why the symmetry is so nearly perfect to begin with. Two circulation states of the same geometry, equally valid, equally stable, produced with equal probability whenever the vacuum has enough energy to form the structure at all. Parity violation. The discovery in the 1950s that the weak nuclear force does not treat left-handed and right-handed configurations identically introduced the first known break in that symmetry. The weak force couples differently to left-handed and right-handed particles, suggesting that nature does have a subtle preference between the two circulation directions, at least in some interactions. Whether this preference is encoded in the topology of the torus or operates through a separate mechanism is a question the toroidal model does not yet answer. But the question itself becomes more precise when posed in geometric terms. What would cause a vacuum to form one circulation direction slightly more readily than the other? The toroidal model places the electron and positron in the same conceptual category as left-handed and right-handed gloves objects of identical geometry whose mirror relationship is not accidental but structural. You cannot turn a left-handed glove into a right-handed one by rotating it in three-dimensional space. The handedness is topological, built into the object at a level that ordinary rotation cannot reach. The same is true of the electron and positron. Their difference is not a matter of composition or scale, but of orientation. And orientation at the topological level is as fundamental as geometry gets. What this means for the broader question of what matter is made of becomes sharper now. If the electron and positron are the same structure in two orientations, then matter and antimatter are not fundamentally different substances. They are the same pattern, expressed in opposite directions. The universe did not need to create two separate things. It needed only one geometry, with two possible handedness states, and the rest followed from symmetry. That is a surprisingly compact answer to a question that has occupied physics since Anderson watched a trail curve the wrong way in a cloud chamber 9 decades ago. The trail curved wrong because the pattern was right, just mirrored, just reversed, running backward through the same geometry that everything else runs forward through. And if two orientations of the same structure account for the electron and the positron, then a natural question forms at the edge of what comes next, not what the orientations are, but what determines how much charge each orientation carries, and whether that amount is fixed by geometry or could, in principle, have been different. When Williamson and Vandermark sat down to compute the charge that would emerge from their toroidal geometry, they expected the number to be wrong. Not slightly wrong. Wildly wrong. Off by a factor of 10, or 100, or 1,000, the kind of discrepancy that would cleanly end the inquiry and let everyone move on. Physical models built on simplified geometry routinely fail by large margins when they reach for specific numbers. The electron's charge is one of the most precisely measured quantities in all of science, confirmed across decades of experiment to better than 1 part in a billion. A rough, geometric model had no business landing anywhere near it. The calculation came back 9% high. Not 10 times high. Not 1,000 times high. 9%. Close enough that the two men looked at the number for a long time without speaking. Close enough that dismissing it as coincidence required more effort than taking it seriously. Close enough that it has continued to surface in discussions of electron structure for nearly 3 decades, not because it is proven, but because 9% from first principles with no fitted parameters, no adjusted constants, no hidden assumptions is the kind of result that refuses to be ignored. To understand what the calculation actually does, start with what the torus is holding. A photon, confined to a closed loop, is not a static object. Its electric and magnetic fields are oscillating continuously, pressing against the boundary of the loop the way pressurized air presses against the inside of a tire. The fields want to expand. They push outward at every point along the circumference, with a pressure determined by the energy density of the trapped radiation. For a photon whose energy matches the electron's rest mass, the specific energy required for the loop's circumference to equal the Compton wavelength, that outward pressure is not small. It is concentrated, stable, and precisely calculable from Maxwell's equations. Something must resist that pressure to keep the loop from expanding. In the toroidal model, that resistance comes from the electric field surrounding the structure. An electric field stores energy in the space around it. The stronger the field, the more energy per unit volume, and the greater the inward tension pulling field lines back toward their source. This is not a new idea. It is the same mechanism that gives a charged capacitor its stored energy. The same tension that holds the electric field of any charged object coherent against the tendency of field lines to disperse. The calculation asks a simple question. How strong must that surrounding electric field be to exactly balance the outward pressure of the trapped photon? Solve for the field strength, and you have solved for the charge, because charge is precisely the quantity that determines how strong a surrounding electric field a particle produces. The field strength needed for confinement and the charge needed to produce that field are two ways of asking the same question. Think of it like a pressure vessel. A steel tank holding compressed gas must have walls thick enough to resist the internal pressure without yielding. The minimum wall thickness is not arbitrary. It is determined by the pressure inside and the strength of the steel. Change the pressure, and the required wall thickness changes with it. The torus works by the same logic. The internal electromagnetic pressure sets the required confinement field strength, and that field strength is the charge. Charge is not assigned to the structure. Charge is what the structure requires to exist. The answer that emerges from this calculation sits 9% above the measured electron charge. 9% is not nothing. It is a real discrepancy, and the model does not explain it away. But the direction of the discrepancy is suggestive. The calculated charge is too high, meaning the model predicts slightly more confinement field than the electron actually produces. This is consistent with what happens when vacuum polarization is taken into account. The vacuum surrounding any charged particle is not passive. Virtual electron-positron pairs continuously appear and vanish in the space around the electron, and these transient pairs orient themselves in the field, positive charges tilting slightly toward the electron, negative charges tilting slightly away. This orientation partially screens the electron's charge, reducing the effective field strength measured at any finite distance. The effect is small but real and measurable. It is part of the same physics responsible for the Lamb shift, the same vacuum activity that Lamb and Rutherford detected in 1947 as a tiny anomaly in hydrogen's spectral lines. If vacuum polarization screens the torus's confinement field by roughly 9%, the predicted charge would drop to the observed value. This is not a proof. It is a consistency. The discrepancy is in the right direction, of the right magnitude, and explainable by a well-established physical effect that the simplified calculation did not include. The historical context makes the 9% more striking, not less. For a century, the electron's charge has been treated as a fundamental constant, a number that simply is what it is, assigned to the particle by nature, with no deeper derivation available. Quantum electrodynamics predicts the electron's behavior with extraordinary precision, but it does not derive the charge from anything more primitive. The charge is an input to the theory, not an output. You put the charge in, and the theory tells you what happens. You do not put anything in and get the charge out. The toroidal calculation attempts the opposite direction. It puts in energy, geometry, and the known properties of electromagnetic fields, things that can in principle be derived from Maxwell's equations and the Compton scale, and asks what charge emerges. The fact that something emerges at all, rather than a nonsensical result, is already notable. The fact that what emerges is within 9% of the real value is the part that kept Williamson and Vandermark from setting the calculation aside. What the calculation implies, if taken seriously, is that charge is not primitive. It is the price of confinement, the field strength that electromagnetic energy trapped at the Compton scale requires to maintain its own structure. A different energy would require a different confinement field and therefore produce a different charge. The electron's specific charge value is what you get when the specific energy of 500,000 electron volts folds into a loop of the specific circumference set by the Compton wavelength. Everything fixed. Everything determined. The charge as inevitable as the shape. Observations across the universe reinforce the rigidity of this value. Gamma-ray telescopes have detected the annihilation signal from electron-positron pairs forming near neutron stars at the centers of galaxies and in the plasma jets launched by black holes across billions of light-years. In every case, the energy of the annihilation photons corresponds to exactly the same electron rest mass and therefore exactly the same Compton wavelength as measured in laboratories on Earth. If the electron's charge were determined by its geometry, and if that geometry is set by the Compton scale, then the universality of the annihilation energy is exactly what the model predicts: the same circumference everywhere, the same confinement pressure everywhere, the same charge everywhere, without exception. The James Webb Space Telescope has observed hot plasmas in galaxies that formed when the universe was less than 1 billion years old environments, where electrons and photons interact at temperatures that existed nowhere in the present universe outside of the most extreme stellar cores. The threshold energies governing those interactions match the Compton scale precisely. 10 billion years of cosmic history have not shifted the number. The electron's charge has been what it is since matter first condensed from the radiation of the early universe, and it has not drifted by any measurable amount since. This universality is what the toroidal model predicts, but cannot yet fully explain. If charge is the price of confinement, and if the confinement geometry is set by the vacuum's response to electromagnetic stress at the Compton scale, then the charge is universal because the vacuum is universal. The same physics operates in a Geneva laboratory and in a gamma-ray burst 10 billion light-years away, because the vacuum is the same medium in both places, with the same stiffness, the same threshold, the same response to the same electromagnetic energy. The electron's charge is not a property of the electron. It is a property of the vacuum's relationship with electromagnetic energy at a specific scale. That is a different way of thinking about charge than physics has used for a century. It does not replace quantum electrodynamics. It does not overturn the Standard Model. It simply asks whether the number that quantum electrodynamics takes as given might have a geometric origin, whether the charge could be understood as emerging from confinement rather than being assigned to the particle that exhibits it. 9% is the gap between that idea and the measurement. Whether that gap closes with vacuum corrections, with a more accurate torus geometry, or whether it persists as a genuine limitation of the model, that question remains open. What does not remain open is the fact that the gap exists and is small. Small enough to ask what is on the other side of it. And that question opens onto something stranger still, because if the electron has a real internal geometry that hides itself perfectly in every scattering experiment ever conducted, then the hiding mechanism itself must be explained. How does a structure with a real size vanish so completely the moment any instrument tries to measure it? There is a paradox sitting at the center of this entire investigation, and it is time to face it directly. The toroidal model proposes that the electron has a real internal geometry, a closed loop of electromagnetic energy whose circumference is set by the Compton wavelength, a scale far larger than the distances that high-energy scattering experiments probe. Every experiment ever conducted at particle accelerators, from the first scattering studies at Stanford in the 1960s to the highest energy collisions at CERN, has returned the same result. The electron behaves as a perfect point, with no measurable internal structure at any scale that instruments can reach. If the torus is real, it should be detectable. It is not detected. How does something with a definite size hide from every instrument ever aimed at it? The answer was embedded in a proposal Louis de Broglie made in the early 1920s, at a time when most physicists were not ready to take it seriously. De Broglie argued that every particle carries an internal oscillation, a frequency tied to its energy, ticking steadily regardless of how fast the particle moves. This was not a metaphor. He meant it literally, a physical, internal rhythm, operating at a rate determined by the particle's rest mass, persisting even when the particle is at rest. For the electron, that rhythm oscillates at a rate corresponding to its rest energy, a frequency so high it completes more cycles in a single second than there are atoms in the observable universe. When the electron moves, something happens to that rhythm that changes everything. Relativity treats time differently along different directions of motion. The component of the electron's internal oscillation that faces forward in the direction of travel gets compressed by the electron's motion, its frequency pushed higher. The component facing backward gets stretched, its frequency pulled lower. Two versions of the same oscillation, now running at slightly different rates, overlapping in space. Two oscillations at slightly different frequencies produce a beat, a pulsation whose rhythm is set not by either oscillation individually, but by the difference between them. Listen to two guitar strings tuned almost but not quite to the same note, and you hear the beat as a slow wavering in the combined sound, a rhythm that emerges from the interference rather than from either string alone. The beat has its own frequency, its own wavelength, its own spatial pattern. And, critically, that pattern can be much larger or much smaller than the physical size of either string. This is the de Broglie wavelength, not a property of the electron's interior. A property of the interference pattern that the electron's internal oscillation creates when the electron moves. And it is this interference pattern, not the torus itself, that every scattering experiment in history has been measuring. The Davison-Germer experiment of 1927 confirmed this in the most direct way possible. Electrons striking a nickel crystal produced diffraction, peaks interference patterns exactly like those produced by waves passing through a grating. The spacing of those peaks matched the de Broglie wavelength with precision. The electrons were not behaving like particles bouncing off crystal atoms. They were behaving like waves whose wavelength had nothing to do with the physical size of the electron and everything to do with its momentum. Now accelerate the electron. As the electron's momentum increases, the forward-facing component of its internal oscillation gets compressed more aggressively, and the backward-facing component gets stretched further. The difference between the two frequencies grows. The beat pattern, the de Broglie wavelength, shrinks. At relativistic speeds, it shrinks so rapidly that it becomes orders of magnitude smaller than the Compton wavelength, smaller than any geometric feature the torus could imprint on the measurement. Imagine trying to measure the diameter of a speaker cone by listening to the sound it produces. At low frequencies, the sound fills a room and tells you nothing precise about the speaker's size. Crank the frequency high enough, and the sound waves become shorter than the speaker is wide, but now you are measuring the wavelength of the sound, not the size of the cone. The two are related by physics, but not equal. A scattering experiment probing an electron at high momentum is in exactly this position. It resolves the interference wavelength, which has shrunk far below the torus circumference, and reports a size of 0, because the interference pattern has no size at that scale, even if the structure generating it does. Researchers at Stanford's Linear Accelerator discovered this empirically in the 1960s and 70s. Firing electrons at atomic nuclei with increasing energy, they watched the scattering patterns carefully for any sign of internal structure, any deviation from point-like behavior, any angular dependence that would suggest the probe was resolving something with dimensions. The patterns showed nothing. Perfect point-like scattering, at every energy they could reach, down to distances roughly 1/10,000,000th the width of a proton. If the electron had an interior that could imprint on the measurement, it was hiding below any scale the experiment could resolve. Murray Gell-Mann had anticipated exactly this situation in the 1950s. He argued publicly that point-like scattering results should not be interpreted as proof of point-like structure, that a particle with complex internal motions could produce interference patterns far smaller than its physical dimensions making the scattering data look structureless even if the particle itself was not. His colleagues were skeptical. A decade later, when scattering experiments revealed that protons contain point-like objects inside them, objects that became known as quarks, Gell-Mann's caution was quietly vindicated. The quarks appeared point-like not because they were infinitely small, but because the probing wavelengths shrank faster than the proton's interior could reveal. The toroidal electron faces the same situation from the opposite direction. The torus has a circumference set by the Compton wavelength. As the electron accelerates, its de Broglie wavelength shrinks far below that circumference. The scattering probe resolves the interference pattern, which at high momentum has no Compton scale features and reports no structure. The torus is not hidden by any exotic mechanism. It is hidden by the same relativistic interference that makes electron diffraction possible at low energies, the same physics applied in the opposite regime. The toroidal model adds one layer to this explanation. The energy circulating inside the loop produces an internal circulation frequency tied to the Compton scale. When the electron moves, this circulation couples with the external motion to generate the two overlapping oscillations de Broglie described. Their interference produces the de Broglie wavelength. The loop itself, the torus, is the oscillator. But the wave it generates when moving is not the torus. The wave is a pattern created by the torus's interaction with its own motion through space. Scattering experiments measure the wave. They never reach the oscillator that produces it. This distinction carries a consequence that physics has not fully absorbed. When a scattering experiment reports that the electron is a point, it is reporting a property of the de Broglie interference pattern at the energy used in the experiment. It is not reporting a property of the electron's internal structure. The two are not the same measurement. They have never been the same measurement. The history of physics has sometimes treated them as equivalent, has read point-like scattering as evidence of point-like existence, but the de Broglie mechanism shows why that reading is incomplete. Scattering probes momentum. Momentum generates the interference pattern. The interference pattern is what the probe resolves. The torus, if it exists, sits behind all three of those steps, untouched by any of them. Astrophysical environments confirm the universality of this mechanism without revealing anything new about the torus's interior. In the hot ionized gas filling the space between galaxies, gas so diffuse that individual electrons travel enormous distances before encountering another particle, those electrons interact with photons in ways that follow DEL, Broglie's wavelength rule precisely. In the plasma jets launched by black holes, where electrons reach energies millions of times, their rest, mass, and their de Broglie wavelengths shrink to almost nothing. The scattering behavior remains perfectly consistent with point-like interference. Across 10 billion light-years of cosmic plasma, the mechanism does not change. The wave shrinks. The structure, whatever it is, remains invisible behind it. What this means, taken carefully, is that the absence of detected structure is not evidence of absent structure. It is evidence that the interference wavelength, at the energies used in the experiment, was smaller than any structural feature the torus could imprint. This is a precise and limited statement. It rules out structure at scales below the interference wavelength. It says nothing about structure at the Compton scale, because no scattering experiment has ever probed the Compton scale without creating new particles and changing the state being measured. The electron's point-like behavior is real. And it is fully compatible with a real internal geometry as long as that geometry generates a de Broglie interference pattern that shrinks to sub-Compton scales before any probe can reach it. The torus does exactly that. Not by hiding, by being the oscillator whose wave, in motion, becomes smaller than the oscillator itself. Point-like behavior and internal structure are not contradictions. They are two aspects of the same relativistic interference, measured at different scales. The scale at which they separate, the scale at which the wave becomes smaller than the structure, is the Compton wavelength. Below it, the probe sees the wave. Above it, the probe would see the torus. And probing above the Compton scale, without creating new particles in the process, is something no instrument yet built has been able to do. The electron hides in plain sight, behind the wave it makes when it moves. And the wave is indistinguishable from what a point would produce, not because the electron is a point, but because the wave that a torus generates when accelerated to high momentum looks, to every probe that has ever touched it, exactly like the wave a point would generate. That is not an accident. It is geometry. And geometry, as this entire investigation keeps returning to, may be the deepest language in which the electron is written. But geometry requires a medium to exist in. A shape cannot float in nothing. And the question that opens just ahead is whether the vacuum, that apparently empty space surrounding every electron, fluctuating in nonlinear and resistant to extreme fields, might be exactly the medium the torus requires to hold its shape at all. Empty space is not empty. That sentence sounds like poetry. It is not. It is one of the most precisely confirmed results in the history of physics, and the evidence for it changes the entire question of what the electron is made of. The vacuum, the space between particles, between atoms, between galaxies, is not a passive backdrop against which events occur. It is an active medium, and under the right conditions, it behaves less like emptiness and more like a substance with measurable properties, stiffness, resistance, and the capacity to produce matter from nothing but stress. To feel what this means, start with a thought experiment. Imagine you could shrink down to the scale of a single electron and hover in the space just outside it, not touching the electron, just existing in the region of space surrounding it. You would not be in nothing. You would be in a region of intense electromagnetic field, the electric field of the electron pressing outward in every direction. And in that field, something strange would be happening continuously. Pairs of particles, one electron, one positron would be flickering into existence and vanishing again, over and over, too briefly to be directly observed, but real enough to affect the field around them. The positively charged partners would drift slightly toward the electron. The negatively charged ones would drift slightly away. The vacuum would be polarizing around you, orienting itself in response to the field, screening the electron's charge from the outside. This is vacuum polarization, not a theoretical construct. A measured effect confirmed in the 1940s when precision spectroscopy of hydrogen revealed that two energy levels which quantum theory predicted should be identical were in fact separated by a tiny but real gap. That gap, the Lamb shift, exists because the electron interacts with the fluctuating vacuum surrounding it. The vacuum is not quiet. It presses back. Julian Schwinger pursued this further in 1951, calculating what happens when an electric field grows strong enough, not at the scale of an ordinary atom, but at field strengths roughly 1 billion times stronger than the field at the surface of the Earth. He found a threshold beyond which the vacuum cannot remain stable. Below that threshold, the virtual pairs flicker and vanish harmlessly. Above it, the field pulls them apart before they can recombine. They become real. Electrons and positrons emerge from empty space, assembled from nothing but the energy stored in the field itself. The vacuum does not merely allow this. It enforces. Push the field past the critical strength, and pair creation is not a possibility, it is a certainty. The vacuum has a yield point, the way steel has a yield point. Stress it below the threshold and it returns to its original state. Stress it beyond and it permanently deforms, releasing new structure. Except for the vacuum, the new structure is matter. This threshold sits at a field strength that sounds abstract until you realize where it appears in nature. The electric field of a single electron, measured at distances approaching the electron's own Compton wavelength, comes close to the Schwinger critical value. Not far beyond it, within reach of it. The electron exists at a scale where the vacuum around it is perpetually near its own breaking point, perpetually close to the conditions under which it would produce new particles from pure field energy. And yet it does not. Something regulates the field before it reaches that threshold. Something keeps the electron stable in a region of space where the vacuum itself is nearly overwhelmed. The toroidal model says, the torus is that something. The trapped photon circulating inside the loop generates an outward electromagnetic pressure. The vacuum generates an inward resistance, not as empty space yielding passively, but as a nonlinear medium pushing back against the curvature of the field. Where the outward pressure and the inward resistance balance, the loop stabilizes. That balance point occurs at the Compton wavelength, the same scale at which pair creation becomes energetically possible, the same scale at which the Schwinger threshold becomes relevant, the same scale that appears in every transition between light and matter anywhere in the observable universe. The vacuum does not merely permit the torus to exist. It determines the size at which the torus is stable. Think of it like a soap bubble. A soap bubble does not have an arbitrary size. It finds the radius at which the outward pressure of the air inside exactly balances the inward surface tension of the soap film. Change the pressure, and the radius adjusts until balance is restored. The bubble's size is not a property of the air or of the soap film alone. It is a property of their relationship, the specific equilibrium they reach together. The torus works the same way, with electromagnetic pressure replacing air, and vacuum stiffness replacing surface tension. The electron size, to whatever extent it has one, is not a property of the photon or of the vacuum alone. It is what emerges when they find their equilibrium. The evidence that the vacuum can do this kind of work, can actively shape electromagnetic fields rather than simply hosting them, has been accumulating steadily. Observations of neutron stars with magnetic fields millions of times stronger than anything producible in a laboratory have detected a phenomenon called vacuum birefringence. The vacuum itself, in those extreme fields, behaves like a crystal that polarizes light differently in different directions. The space around those stars is not empty in any meaningful sense. It is a medium with orientation, with preferred axes, with measurable optical properties that depend on the field strength threading through it. Polarization measurements of the light from one such neutron star, confirmed by observations in the mid-2010s, showed exactly this effect. Empty space had become, under sufficient field stress, something that behaves like glass. Laser experiments have pushed closer to the Schwinger threshold from the laboratory side. Facilities in Europe and Asia have focused light to intensities high enough that photons which in ordinary conditions pass through each other without interaction begin to scatter off one another. Two beams of light crossing in vacuum exchange momentum. They interact through the virtual pairs that the intense field briefly pulls into existence in the crossing region. The vacuum mediates a force between photons by temporarily becoming matter, and the effect grows stronger as the field intensity increases as the vacuum is pushed further from its resting state. If the vacuum can bend the path of light through its own polarization response, then a photon circulating at extremely high frequency, at the frequency corresponding to the electron's rest mass energy, would encounter a vacuum that responds significantly to its presence. The field of the circulating photon would polarize the surrounding vacuum. That polarization would modify the field, which would modify the curvature of the photon's path, which would affect the polarization again. The system would find a radius where these mutual adjustments settle into a stable configuration. That radius is the Compton wavelength. Not chosen from outside, not imposed by a separate force negotiated between the photon and the medium it moves through. This reframes what an electron is in a way that the point particle model cannot approach. A point particle exists in the vacuum. It occupies a location. The vacuum is its background, and the two are separate. The toroidal model proposes something different. The electron is not in the vacuum. It is of the vacuum, a stable equilibrium configuration, that the vacuum and electromagnetic energy reach together when a photon's frequency is high enough to engage the vacuum's nonlinear response. The electron does not sit in empty space. It is the shape that empty space takes when stressed to a specific threshold. Whether this is literally true remains an open question. The toroidal model is not the standard model. It has not been confirmed by experiment in the way quantum electrodynamics has been confirmed. What it has done is connect a set of observations, pair creation thresholds, vacuum birefringence, photon-photon scattering, the Lamb shift, the Schwinger critical field, into a coherent picture in which the vacuum's nonlinear properties are not incidental background details, but the fundamental mechanism by which matter exists at all. The universe, on this account, did not create matter and then place it in empty space. It created the conditions under which empty space would fold into matter, and then the folding happened, wherever and whenever the energy density was high enough to trigger the vacuum's response. The electrons filling every atom in your body are not objects placed inside the vacuum. They may be the vacuum itself, curved into a shape that has persisted for the age of the universe. That persistence is the next question. If the vacuum shapes the electron, and if heavier particles are also shaped by the vacuum in some way, why do those heavier configurations collapse while the electron does not? What is it about the specific equilibrium at the Compton scale that makes it not just stable, but essentially permanent stable for longer than the current age of the universe, stable against every perturbation that nature has thrown at it across 14 billion years of cosmic history? Every particle we know has a lifespan. Neutrons, freed from the nuclei that stabilize them, survive roughly 15 minutes before decaying. Muons, heavier cousins of the electron, born when cosmic rays strike the upper atmosphere, last about 2/millionths of a second before converting into lighter particles and vanishing. The most exotic particles produced in high-energy collisions endure for less time than it takes sound to cross a single human hair. The electron has been measured for over 10 billion years. It has not decayed once. Not approximately once. Not in any of the billions of electrons that have flowed through underground detectors built specifically to catch the faintest sign of decay, detectors running for decades in mines in Japan and Italy, watching and waiting. The lower bound on the electron's lifetime, set by those experiments, now exceeds a number so large that writing it out would require 26 zeros after the 1. For comparison, the universe is roughly 14 billion years old, a number that requires 10 zeros. The electron's minimum lifetime is more than 1 trillion times longer than that. Physics accepts this as a fact. It does not explain it. It simply notes that charge conservation forbids the electron from decaying into anything lighter because there is nothing lighter that carries charge. The lightest charged particle cannot decay into a lighter charged particle because there is no lighter charged particle to decay into. The electron is permanent because it is minimal, the floor of a staircase with no lower step. The toroidal model offers something the standard model does not, a mechanism for why that floor exists and why nothing can fall through it. The geometry of the torus is not merely a shape. It is a topological configuration, a structure whose defining property is not its size or its orientation, but the way its fields are wound around themselves. Think of a loop of rope with a single twist in it, sealed at the ends. That twist cannot be removed by pulling, pushing, stretching, or rotating the rope. The only way to remove the twist is to cut the rope open to break the structure entirely. The twist is not a feature of the rope. It is woven into the topology of the closed loop, and topology does not yield to force. The charge of the electron, in the toroidal model, is that twist. It is not a label applied to the structure from outside. It is the directional orientation of the electromagnetic fields as they wrap around the closed path, a global lean encoded in the geometry that cannot be removed without unwinding the entire configuration. To remove the charge would require the torus to untwist. But untwisting means breaking the topology. And breaking the topology means destroying the structure that carries the charge. The charge and the structure are not two separate things. They are the same thing, described from two different angles. This is why charge conservation and topological stability are, in the toroidal picture, the same constraint. Charge conservation says charge cannot be created or destroyed. It can only be redistributed among particles. Topological stability says the twist in the torus cannot be removed without ending the structure. Put them together, and the conclusion is unavoidable. An electron cannot decay into something uncharged, because doing so would require the torus to untwist, which would require destroying the charge, which is forbidden. The electron is permanent, not despite charge conservation. It is permanent because of it, and because its charge is not a property it carries, but a property it is. To see why this fails for heavier particles, consider the muon. The muon carries the same charge as the electron. If charge is a topological property of a closed electromagnetic loop, then the muon is also a loop, but a larger one, with higher energy, holding more internal electromagnetic pressure. That pressure creates instability. The system wants to relax to a lower energy configuration. And it can, because a lower energy loop carrying the same charge exists. The muon decays into an electron, releasing the excess energy as two neutrinos. The charge transfers intact. The topology is preserved in a smaller, more stable version of the same winding. The electron cannot do this. There is no smaller loop with the same charge. The Compton wavelength is the minimum circumference at which the balance between photon pressure and vacuum resistance can be maintained. Shrink the loop below that circumference, and pair creation disrupts the structure. Expand it, and the loop cannot sustain itself. The electron's size is not a coincidence. It is the only size that works, which is why it is the only configuration with that charge that cannot relax further. In 1957, physicists built the first detectors sensitive enough to potentially observe electron decay. The idea was straightforward. If the electron ever transformed into lighter particles, the transformation would release energy detectable as a faint flash of light in a large, transparent medium. Fill a tank with enough transparent material, water, mineral oil, a crystalline scintillator, instrument it carefully enough, and wait. Decades passed. Progressively more sensitive versions of the experiment were built in deeper mines where cosmic ray backgrounds were lower. One facility in Japan eventually surrounded a tank holding 50,000 tons of ultra-pure water with nearly 13,000 photomultiplier tubes, each capable of detecting a single photon. The electrons in that water, numbering in the tens of trillions, were watched continuously for years. None of them decayed. Not one. The experiment did not fail. It succeeded by establishing, with increasing precision, that the electron's lifetime is not merely long but effectively infinite on any timescale that physics can probe. Cosmic environments have been running a similar experiment for billions of years, at scales and energies no laboratory can replicate. Electrons created in the first minutes after the Big Bang, when the universe was dense enough and hot enough that pair creation was occurring continuously throughout all of space, are still here, unchanged, participating in the same chemical and electromagnetic processes they have always participated in. Electrons accelerated to nearly the speed of light by the magnetic fields of pulsars survive their acceleration intact. Electrons caught in the violent plasma jets launched by black holes, subjected to field strengths and temperatures that would vaporize any ordinary matter, emerge still carrying the same charge, the same mass, the same spin they entered with. The universe has tried to break the electron for 14 billion years across every environment it knows how to create. The electron has not cooperated. What makes the toroidal explanation compelling is not just that it accounts for this stability, it is that it makes the stability feel inevitable rather than arbitrary. The Standard Model records the electron's permanence as an empirical fact supported by charge conservation. It does not say why charge conservation should produce permanence, or why the electron's charge should be topologically locked rather than loosely attached. It simply notes that the conservation law holds and the electron survives. The torus says, of course the electron survives. Its charge is not attached to it, it is woven into it. Removing the charge would mean unweaving the structure, and unweaving the structure would mean violating the conservation law that prevents unweaving. The electron is stable for the same reason a trefoil knot tied in a sealed loop of string is stable, not because it is strong, but because the only operation that would destroy it is logically forbidden by the thing it would have to undo. The deeper question this raises is not about the electron alone. If the electron's permanence follows from the topological locking of its charge, if stability is a geometric consequence rather than an assigned property, then every other particle's instability might also be geometric. Particles decay because their internal configurations can relax to lower energy states without violating conservation laws. The electron cannot relax because its configuration is already at the minimum energy compatible with its charge. The charge is the floor. The geometry is the reason nothing can fall below it. And if geometry determines stability, then the question of why the universe contains stable matter at all becomes a question about geometry, about which configurations of electromagnetic energy are topologically locked, which can relax, and which the vacuum will support indefinitely against every perturbation that nature can apply. The electron has survived every perturbation for 14 billion years. It is still here. Inside every atom of every molecule, of everything that exists, the same configuration persists, the same charge, the same topology, the same balance between photon pressure and vacuum resistance that Williamson and Vandermark's calculation approached from the outside. Stable, complete, irreducible. Not because physics declared it so, but because the geometry left no other option. And that raises the final question of this journey, not about the electron specifically, but about everything the electron implies. If the simplest stable charged particle is a geometric configuration of the vacuum, what are all the other particles? What is matter itself? Not as a collection of objects placed in space, but as a set of shapes that space takes, when it folds tightly enough, at the right frequencies, in the right configurations, to persist. There is a question that keeps forming at the edge of everything we have covered, and it is time to let it arrive fully. Not a question about the electron specifically, a question about everything the electron implies. If a single photon, circulating at the right frequency in a closed loop, can produce something with mass, charge, spin, and topological stability, if all of those properties emerge naturally from geometry, rather than being assigned from outside, then the electron is not a special case. It is a demonstration, a proof of concept. A single data point suggesting that the vacuum is not a passive container for matter, but the medium from which matter is continuously generated, shaped, and held in place. The question is whether the same logic extends to everything else. In quantum field theory, every particle is an excitation of a field, a ripple in an underlying medium that fills all of space. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. The theory works with extraordinary precision. What it does not tell you is what those fields are made of, or why their excitations have the specific properties they have, or why some excitations are stable and others decay in microseconds. The fields are simply there, vibrating, and the particles are their ripples. The explanation ends at the ripple. The toroidal model points one layer deeper. Not as a completed theory, it is not. Not as a replacement for quantum field theory, it cannot be, yet. But as a geometric intuition about what the ripples might actually be, not arbitrary excitations assigned their properties by the theory, but stable configurations that the vacuum and electromagnetic energy reach together when the energy density is high enough to trigger the vacuum's nonlinear response. In condensed matter physics, this kind of thing happens routinely. Inside a superconductor, pairs of electrons couple together through the crystal lattice and begin moving as a single unit with completely different properties than either electron alone. Inside certain magnetic materials, collective oscillations of electron spins propagate through the lattice as if they were independent particles. They scatter, they carry energy, they interact with light. They are not particles. They are patterns. But the distinction between pattern and particle becomes difficult to maintain when the pattern behaves, in every measurable way, exactly like a particle. If the vacuum is a medium and the evidence that it is a medium, with polarization properties, birefringence, and a measurable yield threshold, has been mounting for decades, then the particles in it may be its patterns, not objects placed inside the vacuum. Shapes the vacuum takes when the right conditions are met. The electron is the simplest such shape compatible with electric charge. Its properties, mass, charge, spin, magnetic moment, are the properties of the equilibrium, the vacuum, and a circulating photon reach at the Compton scale. Change the energy, change the geometry, change the way the loop interacts with the vacuum's resistance, and you get a different equilibrium, a different particle. The muon, by this logic, is a higher energy version of the same kind of equilibrium, less stable because the internal pressure exceeds what the vacuum can support indefinitely. It decays to the electron not because something breaks, but because a more stable equilibrium exists, and the vacuum allows the transition. The heavier hadrons, protons, neutrons, the whole family of particles made from quarks, are more complicated configurations involving different field types and different symmetries. The toroidal model does not describe them in detail, but the principle it points toward is the same. If stability is geometric, then every particle's lifetime reflects the stability of its configuration against the vacuum's tendency to relax toward lower energy patterns. Particles don't decay because they are told to. They decay because a simpler shape exists, and the vacuum routes the energy there. What makes this perspective quietly revolutionary is what it implies about the universe's fundamental constituents. For centuries, physics has been a search for the smallest building block, the irreducible piece from which everything else is made. Atoms, then nuclei, then protons and neutrons, then quarks and leptons. Each layer revealed a new set of objects, smaller and more fundamental than the last. The Standard Model organizes these objects into a coherent catalog, and the catalog works. But it does not answer the question underneath: what are those objects made of? What is an electron at the level beneath excitation? The toroidal model suggests the question may be malformed. There may not be a layer beneath the excitation, because the excitation is not an object. It is a configuration, a stable way for the vacuum to be a shape that persists because the forces governing the vacuum support it, and no simpler version with the same conserved quantities exists. The electron is not made of anything smaller. It is the smallest shape the vacuum can take while carrying charge. Observations spread across 14 billion years of cosmic history support the universality of this. The electrons that formed inside the first hydrogen atoms, 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine, without immediately being torn apart by radiation, those electrons were identical to the ones in your body right now. Same mass, same charge, same spin, same topological configuration. 10 billion years of cosmic evolution, supernovae, galaxy formation, stellar nucleosynthesis, and the chemistry of life and the electron has not changed by any measured amount. This is what universality means at the deepest level. The electron's properties are not the properties of an object that happens to be stable. They are the properties of an equilibrium that the vacuum enforces everywhere, always, without exception, because the vacuum is the same medium everywhere, with the same stiffness, the same threshold, the same response, to the same electromagnetic energy. The electron is what the vacuum looks like when it holds charge, and the vacuum holds charge the same way across the entire observable universe. Whether the toroidal model is precisely correct in its geometry is a question experiments have not yet answered. The model is not proven. The 9% discrepancy in the charge calculation remains unresolved. The mechanism by which the vacuum's nonlinear response stabilizes the loop at exactly the Compton scale is still being worked out. Physics is honest about these gaps. But the picture, the model, points toward matter as geometry, particles as vacuum configurations. Stability as topological locking is not a fringe speculation. It is a direction that several serious lines of evidence converge on, from vacuum birefringence near neutron stars to photon-photon scattering in laser experiments to the precise universality of particle properties across cosmic time. The evidence does not prove the torus. It makes the torus worth taking seriously. And here, at the edge of what this investigation can reach, something larger comes into view. If matter is geometry, if the particles filling every atom of every molecule of everything that exists are stable configurations of a vacuum that extends through all of space and time, then you are not an object moving through empty space. You are a pattern, an extraordinarily complex, self-sustaining, self-aware configuration of the same medium that holds the electron in its loop and the photon on its path. The vacuum that fills the space between your atoms is the same vacuum that fills the space between galaxies. The equilibrium that keeps the electrons stable is the same equilibrium that has persisted, unbroken, since the first moments after the Big Bang. You are not separate from the universe observing it from outside. You are a shape the universe has taken a local configuration of the same medium, stable enough to persist, complex enough to wonder about its own origin. The electron does not know this. It simply persists, circulating, holding its charge, balanced between the outward press of its own energy and the inward resistance of the vacuum that shapes it. It has been doing this since before the first stars formed. It will continue doing this long after the last star fades. Inside every atom you are made of, billions of these configurations are running right now, quiet, stable, and older than anything you can meaningfully imagine. That is what the electron is, or might be. A shape that empty space takes when it folds tightly enough. A pattern that persists because the vacuum will not let it go. A small, permanent curvature in a medium that extends to the edge of everything we can see and perhaps beyond. And if that is true, then the boundary between matter and emptiness between you and the space around you is not a wall. It is a gradient, a slow transition from the shapes that persist to the medium they persist in, from the pattern to the field that holds the pattern, from the electron to the vacuum that shaped it, from you to everything. Rest easy with that. You have traveled a long way tonight from the moment two particles vanish into light, through the contradictions of the point model, past the boundary Compton found, into the geometry of the torus, through the mirror symmetry of antimatter, the arithmetic of charge, the hiding mechanism of the de Broglie wave, the nonlinear architecture of the vacuum, the topological permanence of charge conservation, and finally here to the possibility that matter itself is the shape that emptiness takes when it finds its equilibrium. That is not a small journey, and you did not have to take it. The fact that you did that somewhere in you, something wanted to understand rather than simply exist, is itself one of the more remarkable configurations the vacuum has managed to produce. If this journey brought you something clarity, or calm, or simply the quiet pleasure of thinking carefully about something real, a gentle like or a soft tap on subscribe is a warm signal that helps more of these stories find the people who need them. And if you have a thought, a question, or simply want to say where you are listening from, I would be glad to hear it. Sleep well. Breathe slowly. And remember, the vacuum holding you in place tonight is the same one that has been holding the electron in its loop since before the first star learned to shine.